The next topic is excess 3. Excess 3 is nothing but adding 3 to the decimal number, and then we are finally writing the value as binary number. So 0 plus 3 is 4. 0 plus 3 is 3. Sorry. 0 plus 3 is 3. So the final excess 3 code will be the binary value of 3. Now 1 plus 3 is 4. So the final excess 3 code will be 4. Now 2 plus 3 is 5. Final excess 3 code will be 5. And just like that, excess 3 is available only between 0 to 9. This was used in ancient digital electronics, not now. So this is basically used as a error detection correction application, but we have advanced to many other error detection codes, and this is one of the important codes because this was one of the ancient decimal to excess 3 code. Now next is gray code. So now to convert a binary number to gray number, we have to, let's just say for an example, this is a binary number and we have to convert to gray. Now we have to use XOR operation. Now retain the first digit, like 1 is retained as 1. Now we have to convert this 1, where 1 is retained as 1. So 1 and 0, we have to do a XOR operation to 1 to 0. What is 1 to 0 in XOR operation? It's 0. Now 0 to 0 XOR operation is 1, and 1 to 1 XOR operation is 1. 1 to 0 XOR operation is 1. So the final value will be 1. So this is the converted gray code, and this is the binary code. Just like that, we have to convert. We can convert binary codes from 0 to 15 or 0 to the 30, like that. It doesn't have any limit like excess 3 code. This is one of the advantage of gray code. Now logic gates. Logic gates are essential components in digital electronics, performing basic logical functions. These gates process one or more input signals and generate single output based on the particular logic rule. Different logic gates are represented by distinct symbols and circuit diagrams, which make understanding their operation much easier. Now, these are the logic gate symbols. So for AND gate, it is A dot B. The input is 0. The both inputs are 0. Then output will be 0. The both inputs are different. The output will be different. The both inputs are same. The output will be same. Now for OR operation, if only one of the input is 1, the output will be 1. One input is 1, the output will be 1. Both inputs are 1, the output will be 1. For NOT operation, if we give the input as 0, the output will be 1. Then the input is 1, the output will be 0. For NAND, it's complete opposite of AND operation. If both the inputs are 1, the output will be 0. Then next for NOR, the complete opposite of OR operation. If both the inputs are 1, the output will be 0. One input is 1, the output will be 0. One input is 1, the output will be 0. So both inputs are 0, the output will be 1. XOR operation means if both the inputs are same, the output will be 0. So both the inputs are different, the outputs will be 1. XNOR, it's the opposite of NOR operation. So if both inputs are 0, the output will be 1. The both inputs are different, the output will be 0. The both inputs are same, the output will be 1. Next is Boolean algebra. These are some of the Boolean algebra laws, and if you are going to prove these laws, you are going to use the truth table. This is the identity law. A plus 0 is equal to A and A dot 1 is equal to A. Now we are gonna prove using truth table. Let's say the input is 0, and if we add 0 plus 0, the answer will be 0. So this identity law will be proved. The identity law will be truth. Next is null law, then idempotent law. Like A plus A will be A. This doesn't contribute to just 2 digits. It can be A plus A plus A. The final answer will be A. Next A dot A dot A. The final answer will be A. Next complement law. Let's say the input is 0. A, then the complement of 0 is 1. So if we add 0 plus 1, the final value will be 0, will be 1. So next, if you multiply the A and A complement, the final value will be 0, no matter what the input is. Next is the involution law. We are seeing A, then A bar, then A complement, the whole complement. So the final value will be equal to A. Next, the commutative law, then associative law. Associative law, commutative law, and distributive law are the three important laws when it comes to Boolean algebra. These three laws are frequently used in Boolean algebra. Then we have absorption law, then redundancy law, then De Morgan's theorems, and these are some of the important Boolean algebraic theorems. Next, the representation of Boolean algebra is of two types: sum of the products and product of sums. That is, representing the product terms using OR operation, that is addition operation, is called sum of the products. Now, representing the product terms, representing the sums terms using the AND operation, that is product terms, is called product of sums. SOP is always built using min terms. PO is always built using max terms. Min terms are nothing but the winning combination, that is the output will always be 1. Well, max terms are nothing but the losing combinations. The outputs will always be 0. Now, as I said, min term, the outputs will always be 1. If for max term, the output will always be 0. Now, this is one of the example for Boolean expression. Now, let's just say this is the given Boolean expression. We have to reduce it. First, we're using distributive law. The distributive law means we are using the law. So, we are multiplying this inside a plus b into a plus c. So, first we're multiplying inside a into a into c, is b into a, b into c. Now, a dot a is a. Now, a dot c will come as a dot c. A dot b will come as a dot b. B dot C will come as B dot C. Now, A dot C is equal to A as per absorption law. A dot B is equal to A as per absorption law. So, A plus C is equal to A. A plus AB is equal to A. We can simplify this finally as A plus BC. Now, final simplified answer for the given Boolean expression will be A plus BC. This is one of the examples for Boolean expression reduction. Now let's see about K-maps. So these are some of the important rules of K-maps. No zeros are allowed in K-maps, and you should not group diagonals. We should only group ones. We should only group nearby values. No diagonals are allowed. Only power of 2 cells in each group. The group should be as large as possible, and no overlapping is allowed. Wraparound is allowed. Fewest number of groups are possible. Now we'll just see how they're represented as two variable key map is represented as this because two variable means 2 power 2, so totally 4 cells: 0 1 2 3. So it's represented like this or this. In sums we will mostly be using this format. It can also be represented like this. Next we having three variable k map. So 0 1 0 0 0 1 1 0 1 1 a b c. Now, 4 variable key map is represented with 16 boxes because 4 variable means 2 power 4, which is equal to 16 boxes. We are representing a 16 boxes. This is 0 0 0 1 1 0 1 1. 0 0 0 1 1 0 1 1. 0 means the letter will have a bar over it. If it's 1 means the letter will represent it as 1. Like this. So let's see an example. So if we are given a Boolean expression value like this and we are used to reduce the Boolean expression value using K-map, we have to write we have to draw the two variable K-map. So this is 0 1 0 1. So in which number we have given A bar B bar. So in that box then we are putting 1. Then A B in that box then we are putting 1. We cannot group the diagonal, so we are grouping it as individual values. So a bar b plus ab is represented as a xor b. This is represented a xor b, so we can write it as a xor b. Now like some 1 comma 3 is given, so we are putting 1 comma 3, one in only one box and 3 box. So this is the 1 box and this is the 3 box. We are grouping it together. We will be getting a bar because it has 0 and b. A bar B plus AB. It is represented as common is A plus A bar. So into B. B is taken as common. A plus A bar is 1 and we'll finally get the answer B. Now for 3 variable K map, we will be having 0 to 8 because 2 power 3. 3 variable K map. And we are putting ones in only in this values in question, in the value that is given in the question. So 1, 3, 5, 1, 7. We are grouping it as 1 and then we are writing the Boolean expression. We will simplify using the Boolean laws like taking common and finally we'll get the answer as C. And if we are having corner values, we can all group this as 1. We can group this as one value and then finally we'll get the answer as C bar. We'll get the answer as C bar. Next, 4 variable K map. We are writing 1 only in these values: 1, 3, 5, 7, 9, 11, and 13, 15. Now we are grouping this as 1 because we cannot group this as 4 and 4. It will take long process. So we will group this as one value, and all these value has a common of d. So we write it as d. This is the 4 variable. Okay.